Boker Tov and good morning to all. Last time we defined what is an inner product. We started with the Pythagorean theorem and little by little tried to understand it, which led us to the scalar product and then the inner product. We saw a couple of examples of inner products, and in particular saw that sometimes you can codify some nice properties of the vector space using the inner products. And what I like to do today is talk about some basic properties of inner products. And these basic properties will later on let us show that lots of our intuition, lots of the results from basic Euclidean geometry is still true in general inner products. Okay, so let's start. And of course, let's start with a reminder. So an inner product is a vector space over the complex numbers or over the real numbers if you want. And we need a function which takes two vectors and returns a scalar. And it needs to satisfy three conditions. First, it is non-negative. If you multiply a vector by itself, it is non-negative. And in particular, the multiplication v times v is 0 if and only if v is the 0 vector. It should be Hermitian. So if you multiply v times w and w times v, it's the same up to complex conjugation. If you're over the real numbers, then they are just the same. And finally, it is linear in the first variable. It is distributive in a sense. So if you fix the second variable to be w, then it is additive and scalars come outside. Okay, this is the definition of inner product. So today I want to start with one of the most basic property. We know that it is linear in the first variable. The question is it still linear in the second? And the answer is not. It is not linear. It is semi-linear. So it is additive. If you fix the first variable, it is additive in the second variable. However, if you multiply by alpha the second variable, the alpha goes outside but with complex conjugation. Okay, so it is almost linear, it is semi-linear. In particular, if we are over the real numbers, then it is just linear. So linear in the first and second variable. If we are over the complex numbers, then suddenly we need to add the complex conjugation. Now this complex conjugation is quite important because we keep talking about taking the squares. And before, when we talked about real numbers, if you take a square of a real number, it is always non-negative. However, if you take the square of a complex number, in general, it is not even a real number, let alone a non-negative number. However, it is always true that if you take a number, a complex number, and you multiply it by its complex conjugation, this is always non-negative. So this semi-linearity came from this fact. If you want something non-negative, and if you want it, because in the end, this is going to be the length, so we multiply a number by its complex conjugation. Okay, so we want to show that this is semi-linear, and just like with your standard basic linear algebra, there is a more compact way of writing it. So you just take alpha v plus w, and the alpha need to go outside, and the addition need to open up. Okay, so this is indeed a more compact way of writing it. However, I would suggest against writing it like that, because in general you take two distinct things, the fact that it is additive and the fact that scalars come outside with the complex conjugation, and you mix them up together, and this can lead to confusion. So I saw a lot of students lose points because they confuse themselves like that, and in particular for this semi-linearity. And also for the proof of this property, when I initially wrote it, I got confused and wrote the wrong letters for the wrong vectors. So do with it what you want. Okay, so now I want to prove it. So we want to start with the inner product of u with alpha v plus w and end up with the complex conjugation of alpha times uv plus u times w. Okay, since this course is still on the more basic side of mathematics, I want to put a little bit more emphasis on how you go around and prove results like this. And what I want to use today is a very basic trick, works in many places, in particular in algebra. And this is what I call the puzzle trick, because basically we think about this proof as pieces of puzzles, and we just look for pieces of puzzles which fit together. Okay, so let me show you what I mean. This is my first piece of puzzle. We have u and we have alpha v times w. And if I see the properties that I have, these are the other pieces of puzzles that I can use. The one which most fits the basic piece of puzzle is the linearity in the first variable. Right? Because we have linearity here, we have linearity here, and this is how they fit. However, the linear in the first variable is not enough for the linearity in the second variable. And luckily for us, we have a second puzzle piece, which is the fact that it is Hermitian. Okay, so I'm going to use the Hermitian in order to move the second variable to the first variable, then use the linearity. Okay, so let's see how it works. I first use the fact that it is Hermitian, switch between the first and second variable, then I use the linearity. Now I use the fact that the complex conjugation by itself is semilinear, right? It is additive and the alpha comes outside with the complex conjugation. So this is what we get. And finally, we can use again the fact that it is Hermitian to get what we want. Okay, so this is a very, very basic proof. Again, this is not difficult, but the idea is that you just look at the pieces of the puzzle, just try to fit them together with even out any intuition. This is a nice trick that works in many cases. Okay, so this was the semilinearity. So the second property is what I call the zero vector property, which says that a vector is zero if and only if v times zero, w is zero for every w. And notice that we have two types of zero here. The one on the left is the zero vector, the one on the right is the zero scalar. This is an actual number. Now this is a very interesting property. The proof it will be simple, but as a property it is interesting because the left-hand side tells us something about the vector itself. The right-hand side tells us something about how it behaves under multiplication. Right? So moving from the left to the right seems simple because if something is zero, then zero times everything should be zero. Moving from the right to the left, this is the interesting part because in many cases we will know something about the multiplication, about the inner products, and somehow from the information about the inner products we say something about v. Right? This is like the duck test. If something quacks like a duck, swims like a duck, and looks like a duck, it should be a duck. And this is exactly what happens here. If something behaves like a zero vector under multiplication, under the inner product, then it should be the zero vector. Okay, let's prove it. So we start with the first case. So we start with v equals 0. And again, like before, I want to do the puzzle trick. So I want to look at v is the 0 vector and which puzzle piece fits with. So from these four pieces, the one which fits it the most is the non-negative, right? Because it already has v equals 0. However, the only thing that it gives me is that v times v equals 0, and I want to show that v times w is 0 for every w. And it's hard for me to see how just from v times v I get v times w. Okay, so maybe non-negative is not enough. The fact that it is Hermitian doesn't really help because it moves stuff from the left to the right and back, so I don't want to use it. And finally, I have linearity. Now, linearity doesn't have v equals 0, but it is really connected to it. Because if you remember, the fact that a number is 0 is defined using linearity. Okay, so let's remind ourselves. So saying that v is 0 is just saying that v plus u is u for every u, right? It is neutral under addition. And again, you should look that both of these conditions are very similar, right? The left-hand side says something about v itself. The right-hand side tells something about how v behaves, right? Above this is how it is, how the inner product behave, and below how the addition behave. Okay, so they are very similar, and not surprisingly, we can use it in order to show to prove it. Okay, so v is 0 if and only if v plus u is u for every u. And there is a bit more compact way of writing it that v plus v equals v. And let's use it. So v times w, now it can be for every w, is v plus v times w. And now I can use the linearity, which is v times w plus v times w. And this is true for all w. So notice that all the inner products here are the same, and this is now an equation of scalars. So I can cancel the inner product of v and w on both sides and just get that 0 equals the inner product of v and w. So again, they somehow use the linearity in order to show. Okay, so this is the first direction, but before I move to the second direction, I want to tell you that you actually already know this proof, because if I fix w and say t of u is the inner product of u and w, then because of the linearity, then t of u is a linear map. And then what we ask is, what is t of 0? So we said, okay, t of 0 is t of 0 plus 0, which is t of 0 plus t of 0, right? We can open up the linear map. And now you can cancel it and get that t of 0 is 0. Or in other words, every time you have a linear map, it sends 0 to 0, which is something that you already know from your basic linear algebra course. So in a sense, we reproved it, but it seems more complicated. Or if you want to look at it the other way around, if you take our original proof and you do it a little bit more abstract, you think about it just as a linear function and not as an inner product, then suddenly it is much easier to do. And this is actually the good part of abstractization, right? You throw away the noise, and then suddenly it is easier to do. There is the bad part of abstractization, and I will try not to do it, but this is the good part. Okay, so this is one direction. Let's talk about the second direction. Now we start with v times 0 equals 0, and we want to show that v itself is 0. And again, if you think about the puzzle trick, I'm looking for the only place which fits this. And again, this is the non-negative part. And unlike before, this time we can use it, because if v times w, if the inner product of v and w is 0, and this is true for all w, then the inner product of v with itself is 0, and then we can actually write that v is 0. So again, we have these two directions, not so difficult, and we get the zero vector property that if something behaves like a 0, it must be a 0. Okay, let's continue to the next property. And it's very similar, and it talks about equal vectors. And it says that two vectors are equals, v1 equals v2, if and only if v1 inner product with w is the same as the inner product of v2 in w, and for every w. Right? So again, if they behave the same, they must be the same. And this is going to be really important because in many cases we only have the information about the inner products, and we somehow want to extract information about the vectors themselves. Okay, so how are we going to prove it? And here as well there is a nice trick, and the trick says as follows: if you have an equation and you have a problem both on the right and the left side of the equation, and if in a sense they are same type of problems, then maybe you should move everything to one side. So for example, instead of v1 equals v2, you look at v1 minus v2 equals 0. So suddenly, instead of two problems, you have something equals 0. Also on the right side, we get the inner product of the first one and the inner product of v2 times w. The difference is 0. And now we can suddenly use the linearity, which again, what does linearity do? It takes two problems and mixes them up together, and these are two problems of the same kind, right? Not like before. And now suddenly we have on the left, v1 minus v2 is 0. And we want to show that it is if and only if the inner product of v1 minus v2 is w is 0, which is exactly the zero vector property. So again, we started with this sort of problems. We change it to the homogeneous version, right, equals 0. And this takes us back to the zero vector. Okay, so now we have these zero vector properties and the equal vectors property. And I'm sure you have seen many similar proofs like this before, that you want to say that two objects are the same, and this is if and only if the difference is 0. And the proofs were not really hard. However, I think that the idea of the proof is really interesting. For example, let's say that I give you the following equation. I tell you that the integral of f times h is the same as the integral of g times h for every h. And I want to tell you that I want you to show me that f equals g. Right? And if I look at something like that, this is scary. Suddenly I have two integrals and I have three functions and I need to do something with it. I don't know even where to start. However, once we think about it as inner products, once we throw away the noise, then suddenly what we see here is that we have two functions, we have f and g. They behave the same under this weird integral. And we want to show that if they behave the same, then they must be the same. So this is exactly what this equal vectors property, exactly what this zero vector property. Okay, so these are very simple yet very important properties. I want to move now to an exercise. So let V be a finite dimensional vector space over the real numbers or the complex numbers. Show that there exists some inner product on V. Okay, whatever inner product you can find. Now you should stop the video and try to prove it by yourself before we do it together. However, I want to tell you why I put it as an exercise and not a property. And the reason is that whenever you want to study an object, like this finite dimensional vector space, you want to study its properties. You don't want to just invent new properties that have nothing to do with the object itself, right? So here we tell you that there is some inner product. If it is not related by any way to the other properties of V, it doesn't matter. Now, the reason I want to do this exercise because the proof itself is interesting. Okay, so I hope that by now you actually stop the video and try to prove it yourself. And now we can move to try to find a solution together. Now, the trick to this solution is something that you already know from your basic linear algebra course, is that if you give me any finite dimensional vector space over the real numbers, then up to renaming it is the same as R to the n. And this is very interesting because on R to the n we already have an inner product, we have the standard inner product, so we can use it and up to renaming define an inner product over V. Okay, let's make it a little bit more formal. We have some linear map from V to Rn, and it is an isomorphism. This is again from basic linear algebra course, and it takes any vector V to T of V. So we now can define the inner product of V and W to be the standard inner product over Rn of TV and TW. Right? So again, we just rename the inner product, but in the names in V. So take it as an exercise to show that this new definition is indeed an inner product, and as an extra exercise shows that even if it is just injective, it is just one-to-one and of course linear, then it is still an inner product. Right? Because the idea is that if it is linear, if it is injective, that it is surjective, it is onto its image, right? So it is an isomorphism on its image. Okay, now as I said before, by itself this result doesn't mean anything because if T can be everything, then it doesn't mean anything. However, in many cases, maybe you have some vector space V which you want to understand but you don't. But on the other hand, you have this vector space R to the n which you do understand quite well, and you have this interesting map that you define between V and Rn, and it has some importance, it comes from the structure of V, then suddenly this new inner product means something. Okay, so I want to give you just a little bit of a taste what happens there. So let's say that V is actually R to the n. Okay, so they are vectors of length n. Then you know from basic linear algebra that every linear map between R to the m to R to the n can be written as a product by some matrix, as a multiplication by some matrix. And then the inner product of V and W, by definition, is the standard inner product between AV and AW, which is, by definition, again, AW transpose times AV, which is W transpose times A transpose times A times V. And suddenly, in a very natural way, we got this matrix, A transpose times A. Now, if you did anything inside numerical algorithms or maybe machine learning, there is a very good chance that you saw these types of matrices, right? You take A transpose times A. And maybe no one told you the reason for this matrix. And this is exactly the reason. You had one vector space, one problem that you wanted to understand, and the way you did it is by mapping it to another place, another vector space that you understand quite well, and what you needed to pay for this transformation is this matrix, this A transpose times A. Okay, so we will see this matrix again and again and again in the future, but for this video this is enough. So we now have a little bit of basic properties for the inner product, and what we want to do next is to talk about the square root of V times V, right? The geometric part of the inner product, what we want to think about as the length of the vector, right? So we know the properties of the inner product as product of two vectors. We'll go to the inner product of a vector with itself.